My name is Simon Yardley. I've worked for Husco for 10 years in engineering, account management, and now business development roles. I currently reside in Milwaukee, Wisconsin. As you probably tell by the accent, that is not where I am from. I'm from the UK, where I spent the first 7 years of my career with Husco. And since coming here, really opening up the market for what we're going to talk about today is what one of my key tasks has been. Alongside me should be Ben Holter, who is the technical lead of this whole project. I'm going to do my very best to give you a technical introduction to what we have done, but there is a line where I know, and when I get there, I stop. And then feel free to reach out to Ben. He's busy back in Wisconsin laughing the fact that I have to go through technical slides that he put together, but I will do my best. So the presentation. One slide on Husco, just to introduce us and the project and why it came about. The problem that we have in the market, there's a lot of things going on. I imagine the group here really know about that. Control of an excavator. We have a lot of history in how to control these machines, and I just want to raise a little bit about our theory of the control of an excavator. The project scope, so what we said we would do, the challenges we faced, and there are numerous. EXACTO, that is the name for the system that we created to deal with these challenges. The results of what we did, and then the wrap-up. Before I get into it, I will mention this is Friday afternoon. We are in Las Vegas, and I have bought prizes all the way from Wisconsin. So this is for nice questions. So there is beer here for nice questions and being nice to me. So that I'll just put that there so everybody can see that. So hopefully the presentation should go very well. Husco, so we design and manufacture hydraulic components and systems. So components from very small solenoids, from cam phasing valves on engines, all the way through to large main control valves. We design, develop and manufacture these complete systems. This year we will be a $500 million company. We only sell to OEMs, so direct to OEMs. Of those OEMs, we have what we call partner suppliers. So Caterpillar, John Deere, HYG on the off-highway side, Ford and General Motors on the automotive side of the business. They really use us as an extension of their engineering departments. That's how integrated we are with these companies. Everything we produce is bespoke to them. We don't have a huge catalogue that you can flick through and say, oh, I want that valve, that color, that flow. And so we have to have very deep engineering relationships to achieve that. We have 6 global manufacturing sites worldwide, 3 in North America, 1 in the UK, India and China, and about 1,500 employees. A very high degree, a very high engineering count within the company, about 350. I think this is probably closer to 400 degreed engineers within the business, and we're still family owned. So our chairman and owner, Gus Ramirez, bought out the company in 1984, and in 2012, the management went to his son, bringing a lot of new energy into the company and the developments we make. So a really interesting story for the company and a great global company to work for. The problem statement that we're faced with, as many people at this whole conference in here and outside in the lots will know, there really has been anemic gains in construction productivity. So the orange line along the bottom, that is construction. The midway line is the total economy, and the top line is manufacturing. So manufacturing made a lot of gains in productivity, and you can imagine it when you see robotics coming in, automation. We use it within our manufacturing. You see this live. For construction, for various different reasons that a lot of us know about, and I'll talk about a few, there's been really small gains in productivity. A couple of those reasons. So the reduction in skilled labor. This is a global problem now. It used to be specific areas, but again, you talk to the guys outside, getting the availability of good, reasonably priced skilled labor. It's a challenge, a real challenge. Increased pressure on capital utilization. These are very big macroeconomic figures, but a 1% increase in productivity would be a $100 billion global annual saving to the construction industry. So very small gains will have very big effects, such as the size of the construction industry. Those are the negatives. The positives. There's a lot greater acceptance of technology on the work site. Whether we blame the iPhone with the bringing together of many technologies into one very easy user interface, but just in general, there is a lot more acceptance. Again, very macroeconomic figures, but we all know that the acceptance of robotics, drone use for surveying can save time, can save safety, doing remote surveying. There's a lot more acceptance and a lot more demand from the end users, these features and what they want from their systems. Husco has a bit of history in this. On the motor grader, we used to have a mechanical valve that was just on there doing the blade tip control. And then we found out that the Topcon, Trimble, Leicas of this world were putting a whole EH valve on top of our valve just to get the blade control, because they wanted to automate the blade control. If you could make that machine go from 3 miles an hour to 6 miles an hour, and if you could save one pass because you were doing automatic adjustment of the blade, then that's worth a lot of dollars. Whichever currency you want to use, it's worth a lot. And they were spending a lot of money putting these kits on top of ours. Exactly the same story with bulldozers. A slightly different machine form, a slightly larger valve. So what Husco has become very successful is when these companies, the OEMs, have made the change from a mechanical system or pilot system to an electro-hydraulic system. Husco has been there picking up business because of the knowledge of these components that we make in-house, the small cartridges, through to the main control valve systems, bringing together all of that knowledge in one place. Now, the excavator. And I'm going to tell a little story about an Italian artist. This is not the place where you think you'd hear the story about an Italian artist. In the 14th century, there was a guy called Giotto. Giotto claimed that he was the best artist in all of Italy, and the Pope put out a competition to say, send me all your best work, and the best artists, you can paint my new artwork within the Vatican. So everybody made all these amazing drawings, sent them in. Giotto, he drew a perfect circle, freehand, no stencil, perfect circle, sent that in, and he said to the courier, tell the Pope, that is why I am the best artist in all of Italy. Drawing a perfect circle is really, really difficult for any human being, almost impossible. Husco likes a challenge, and the VP of Engineering challenged the engineers, okay, you reckon you're smart. I want you to draw me a circle with an excavator. Go on, see what you can do. Drawing a circle with an excavator is really, really hard. I know, and I'm about to embarrass myself, because this is my attempt. I have about 10 years of experience of driving excavators. I'm not an expert operator, but I certainly know how to handle them. So this is me at our Walkershire site. This is about a 15-second long exposure of me trying to draw an excavator. And as you can see, this is not a circle, and I would not impress any Pope at all with this type of performance. So this was our challenge. Can we draw a circle with this excavator? The project scope, we have to fit a system within a standard excavator to enable digital control of this machine. The deliverables have to be safety, number one. We are never going to be in business if this is an unsafe system. We have to integrate with the existing hydraulic circuit. We can't take the whole main control valve out, the joist, take everything out and put in all new stuff. That isn't realistic. That's a science project. Husco has not got to where it is by doing science projects. Performance. We wanted to use full speed automated grade. So we challenged ourselves to use 100% of the velocity available from that machine at what we would call a precise grade. So a flat grade at plus or minus 25 millimeter tolerance. So that was our performance target. The machine, so this was a rental machine, 4 years old, 4,000 hours. So this has had a hard life, this machine. This is not perfect. It was a little bit rattly. We had to fix a few things on it to start with. And it's a negative control hydraulic system. What this is a really good representation of what's out in the market today from a machine and the standard excavator that's out there. Currently, probably 95% of all excavators in the 15 to 70 ton range have a pilot operated system on them, either negative control or positive control. There's not many EH systems out there in the market today. So this is a really good representation to do the project on. The path planning. I mentioned about the acceptance of automated features certainly within the manufacturing market. And there is a lot of research around robotic control and how you develop autonomous systems. So we didn't need to create that from the start. The knowledge is already out there, the G code that's used to program robots, but that they have servo-operated arms that when you say, I want to go at this velocity or this speed, and I want to get to this point, they get there. They have one motor or one power source per effector, which is going to guarantee it gets it there, which is very easy from a geometric point of view. The excavator is not like that. So not only do we have what we're going to look into is a very flexible system that's been tuned for an operator, not for a motor. We also have a lot of other things going on. So the grey line at the bottom of the sketch there, that is the trajectory that we want. So that's the combined bucket tip trajectory. But in doing that, you're balancing 3 items at once, the boom, the arm, and the bucket, to get the precise line. And each one, as it goes through that motion, we have a little sketch shortly that shows that, each one is doing a different velocity. It's not a fixed speed you're trying to keep through that. So when you're doing the path planning and doing the control, these are the elements that have to go in there. And it's what has made this challenge so far from using, say, the code that operates a robot to the performance you get from an excavator. This is one of the reasons why it's become so difficult. Think through a little bit more of the detail. So we recorded an excavator doing a 10-minute function. So just a bit of grade in hard gravel and a little bit of dump, so that we could get the data exactly from what that machine was doing. We can't see at the bottom there. It's pump flow is at the bottom and pump pressure is along the top. And what you get is the human being that's driving these machines, they're a big compensator. They're commanding because they know they've got these very good analog controllers at the end of their arms linked to the joysticks. They know what they want, but they are always over-commanding what that machine can do. You never have a pump, an engine, and a system big enough to command what the operator wants, either through a single service or multiple services, like I mentioned with the 3 working at once. This is what the map looks like. So in red, we have pump 1, and in blue, we have pump, other way around. Red, pump 2, blue, pump 1. And these are the exact maps that are going on during that grade. Nearly all of these systems are 2-pump systems. If you go onto the smaller excavators, they're 3-pump systems, but you see a very similar map. And what's interesting that you can see along all of this, it's still a long way from where the operator command is. So that balance, that compensation that's going on, all of that balance is going on by the operator. It is the operator completing that movement. It's not a mechanical one or a software one. Because we know hydraulics, we know the systems, we know that top line there, that is your pump pressure limit. The curve you see, that's pump power, which is a proportion to the engine and the torque that you have in your engine. And then at the bottom, that is your pump flow, so the maximum from those pump flows. So you're balancing all of these items are getting balanced at once by that skilled operator, of which there's getting less in the world. So what this excavator looks like. Sorry, some of the wording has been lost there. So as it goes along this system, so the red are the actuators. And so, as I mentioned, the different velocities that are going on, you can see that the boom, so in light blue, it goes up and then it actually goes down. So it changes direction. There's no robot that really changes direction halfway through and has a linear cylinder which has a greater area one side to the other. This is a really complicated movement, all to achieve a flat line, let alone the circle that I showed you earlier that I'm really bad at doing. So with the 2-pump system that you have on here, all of this balance has to be done by the machine, and that has taken probably 20 to 30 years to do all of that tuning of the system to be able to get an operator to do this performance. We then had to overlay it with software or a digital interface to then bring this and to make it so that we could bring in our extra functions. Another challenge is the speed in which you can control it. So in the top graph, we have the amplitude versus the frequency. The different elements, the diamonds you see along there, that's the natural frequency of the different elements of the excavator. So the whole machine this is logarithmic, so sits at around about 1 hertz, the boom 2, the arm at about 5 or 6, and the bucket out to about 9 hertz. So that's the natural frequency of those elements. As you increase the speed, or the amplitude, as you increase the amplitude, I get it right, as you increase the speed along the bottom, your amplitude naturally goes down. This is a natural effect of hydraulics. And all in red there, you see a conventional mobile hydraulic hardware that is available. So what is on the machine today? This is the most that you can do. And as you can see there, at some point, the amplitude that is available drops below the natural frequency of the machine. When that happens, you are not in control, or you cannot be in control, because the frequency, there's no match up. So you either get resonance or you just cannot control it. A slightly nicer analogy to think of when you look at this is a washing machine. So a washing machine, the faster it starts, the better. It needs to get to a very fast speed. On the way there, it'll go through this rumbling stage. That's when it's not in control. So when it's slow, it's okay. It goes through the rumble, then it gets to fast, and then it's in control of its own natural frequency. This is exactly the same as what we are seeing here. The other element, which is on the lower graph, is our reaction speed. So the dots that you see going along the bottom and the two parts of the graph, that is the latency. So how quick we can react. So again, in the human system, as in your brain, you're part of the system and you have very, very fast latencies to be able to react to what you see. We have to over-exceed those to be able to over-command the system. So that's just a review, and that's with a standard hydraulic system fitted to any excavator today. So the system we have that we named EXACTO. So to start with, it was a 3-function system, so it could control boom, arm, and bucket. Safety, absolutely paramount. So any failure, any electrical breakdown, any other system, the system has to switch back to operator control only. That's the only way you can do a safe system. We're listening. We have pressure sensors on both the operator side, so we're listening to what the operator is commanding, and on the main control valve side, so that we know whatever signal we're giving to the main control valve is what's being achieved. That's really important for closing the loop. We have various different modes, so operator only or a fully automated control, so that we can either control it or some other party can control the machine. We have all our own components. We'd be a little bit stupid if we built our own system and didn't use Husco's own high-performance controllers, components. And then we had an integrated controller and our work function algorithms. So these were all the elements that we had to put into this system to get the desired results we wanted. It's important to know where we fit into the machine control landscape. As you can see from some of the work we've done, we have certain elements, certain path planning, we have a machine. Husco, that is not the value case for us. But to prove our system did what it could do and how we could really prove our performance, we had to combine all these systems. So from the start of machine control, you have the input, either a user saying, I want to be 1 foot low and I want to come in, or you have a site plan or a BIM system that tells you where that end effector needs to go. That needs to report to a machine interface to tell the operator what's going on, and that needs to go into some form of automation controller that's going to define where all these functions need to be, where all these different boom, arm, and bucket, it needs to tell it where it's going to be. Then it goes into what we call our EXACTO system, so we can convert that need from the digital side of this map into the hydraulic side. We then control the main control valve with the precision that's required, and then it goes out to the end effector. To close the loop, you need to know exactly where the end effector is in space. And that's where there's IMUs or GPS systems out there to bring that back to the automation controller to say, you said I should be here. Am I there? And if not, what do I need to do to get there? So there was already a closed loop on the complete system. For our test work, you'll see it in some of the videos, we did not use IMUs, we used string pots, just because of the speed of reaction, and it's what we had available. There's lots of companies that do very good IMUs out there. Again, that is not Husco's value play. So in this whole landscape, Husco only are looking at a very small part of that, but it's also a very key part to be able to give this digital interface to the various providers to get the control of that system. So the exciting bit, apart from the video and the beer, obviously, are the results. So in blue, you see the EXACTO system, and all these results are directly from the spool within the main control valve. Apologies, I didn't mention that before. So that exactly when we command that spool is when oil starts moving towards that end service, which is where we need to operate. So you can see with the EXACTO system, we were able to push out past the natural frequency of all of the different elements, ensuring that we had the amplitude, the required amplitude for total control past the bucket, which has the fastest natural frequency. Also on the lower graph, you see, although not a huge step change, there was an improvement in the latency of the system. And more importantly, it was pushed further past so that we could get the latency at a lot faster position past the total natural frequency of the machine. And that was part of what our aim was for the system. Well, so here is the machine. Hopefully, when I click this, you should be able to see. So I'll just explain a little. So the operator is on there. He has a laptop in the cab. All that doing is used as a trigger. You'll see the operator takes his hands off the joysticks. This is 100% controlled by the EXACTO system. You can also see the little white box on the top of the cylinder. That's the string pot that we use to make sure we know the cylinder pictures, the cylinder position. So we have just a flat grade is programmed in, and you can see here all the different elements. And the boom goes up, and then it has to come down. The bucket does not move much. Of course, as you've seen from the graph, that's the one with the highest frequency, or the highest natural frequency. He did a good job there and didn't show us his hand, which is good. And so there you can see the grade. And this, from what we see out in the market, is a competitive system because of how we were able to integrate with the system. What the results look like that we've recorded off the machine. So the top one, that is the pressure. Obviously, we're working in a pressure world of the exact system that was on there. So the solid line is the command. So this is what we want to achieve. The dashed line is the actual pilot. So that's what we did achieve. So we run pretty good. We're running almost line on line, which is great, all until you see that this dip that goes down and everything gets a little bit out of shape before it catches itself back up. That is, as you imagine here, sorry for the people that are just listening, that is when the boom goes up and then the boom comes down. We call it the over-center moment. This is really difficult to control, and you're moving your high pressure side from one side of the cylinder to the other. This is a really difficult place, and we've been doing a lot of work in this area in future iterations after this project, but for a first attempt, we were pretty pleased with this. The next graph is the velocity, so the speed of what was happening. And this is how I mentioned in when you saw the graphic working, how the various speed across a whole range that you have to deal with. This is a 5.6 meter grade. The various different speed, the boom, how it goes into the plus and then it goes over center. It actually goes into a minus, the direction in which it goes. These are the balances that you're having to do. And again, we just had a little problem around this over center moment, but we were still pretty pleased with those results. The next one is the really important one. I can tell you the pressures are perfect, but if the grade looks terrible, you're going to tell me it's worth junk. So the bottom one is where the actual bucket tip position is. Our target was a plus minus 25 millimeters across the whole grade. And by and large, we got there. So it's particularly the first 70% is actually plus minus 10 millimeters, which we're really pleased with. When we then come to this over center, we have a bit of a wobble, and then at the very end, it just lifts out. Again, the geometry really plays against you. But for the working position, we were really pleased with the results that we had in this area. So the headline, we had 5 meter grade, the big grade, the total grade of the excavator available in 5.6 seconds. Our target was to be at 100% of the velocity available of that machine, the best that machine could achieve with the best operator pulling the sticks as fast as possible. 5.6 seconds is around about 90%, just over 90% available from the machine. There's 2 reasons for that. One is we needed a little bit more time to tune it to see if we could get there. And we actually had to slow it down a little bit at the start and at the end because it was a bit jerky to start with if we gave it 100% command straight away. And at the end, it clattered into the machine a little bit and quite close to the operator. So we had to slow those down a little bit. But still, 90%, we were pleased with that one. So that's a bit of an overview of what we did, but I know what you're all thinking. That circle, Simon, how did you get on with that circle that you mentioned? Because we're all remembering Giotto. We can't remember your name, but we can remember Giotto. And this is the circle that we came up with. So as you'll notice, this time we've taken Simon, the useless operator, out of the machine, and now it's just EXACTO. So there's no operator in the machine. This is a 14-second exposure. Long exposure with just a little LED light bulb and some flash cans so you can see the movements of the arm at our site there in Walkershaw. We've been really pleased with the results of what the team were able to do. So next steps for us is refine the system performance. We know where there's some challenges, particularly in that over-center movement. Apply some automated commissioning. So this worked really good on this machine. What happens when you put it on a bigger machine, a smaller machine, a machine with a longer boom, all of the various things out there? We need to create a system that doesn't take a month to tune for each one. Again, that is not a viable system to go out into the market. So do we need to do any automated commissioning? That would be an interesting one to think about. And also then expand the number of features. As you've seen, that was 3 function. If you come to our stand, we already had a 4-function version. To bring in, say, if you have a tilt rotator, we've been working on that. But then the next thing people are going to be talking about, that's great. Now can we fully automate the vehicle? Could we do remote control? Now you've got that bit really good. And so that's the areas that we have been looking into. So for myself, thank you very much for attending.